Okay, guys. Now let's look at the log differentiation. Okay. Log differentiation. Let's recall the laws of natural logs. Laws of natural logs. We have three important laws that we're going to use here in log differentiation. But before we go in details with log differentiation, let's recall this log. We know the first one, say if you have ln of A times B, this is equal to ln of A plus ln of B. The second law, say if you have ln of A over B, that's equal to a ln of A minus ln of B. The third one, if you have ln of A and A is to the power of R, you can take this R down and that will be equal to R ln of A. Yeah. Just recap those laws. You're going to use it in log differentiation. Okay. We're finding the derivatives here. Okay, we know the product rule and quotient rule are used when there are just two vector functions. For example, let's say you have your function y. My function y is h of x times g of x. There are two vector functions. So you can easily apply the product rule, you know. Finding the derivative of the product, we're applying that product rule. And if we have a quotient of two functions, as you can see, again here, we have two vector function, h of x, we can apply the quotient rule. And when there are more than two functions in any arrangement, it can be a top or bottom, the derivative is best found by what is known by log differentiation. For example, let's look at this example one. I'm going to do it. Let's say we want to find the derivative of y. Y is a function of x. As you can see, y is a factor of more than two functions. In any arrangement, it can be in a numerator or denominator or the product, but it's more than two factors. You can see the factor function, how many? 1, 2, 3, 4. We have 4 factor functions. So to find the derivative of this, it's best to use what we call log differentiation. You can follow the normal, someone can think of using the quotient rule because it's a function over a function. But let's use a quotient rule. Let's say we're using a quotient rule to find the derivative of this function y. So the quotient rule, if you follow the quotient rule, is going to be a derivative of the numerator while we leave the denominator. But when you're finding the derivative of the numerator, you're going to apply the product rule because the numerator is a product of two functions. Yeah? So to apply the standard derivative like quotient rule in this function, which is a factor of more than two times, it will be complicated. So if you have your function as a factor of more than two functions, so you just apply what we call a log differentiation. Okay, let's use a log differentiation to find the derivative of this function. The first step, we see we have a function y, we want to find the derivative, and it's a product and quotient of more than two terms. So we're going to apply the log differentiation. The first step is to apply ln on both sides. Yeah? Ln of the left-hand side equal to the ln of the right-hand side. Yeah? So ln of the left-hand side, ln of y, equal to a ln of the right-hand side, a to the 5x times sine of 2x over square root of 3x squared plus 2. It's multiplied by tan of 3x. There's your first step, apply ln on both sides. The second step, expanding your right-hand side using the log properties. Yeah. So here we have ln of y equal to, let's expand this using the log properties. You see we have ln of a over b. If you treat your numerator as a and the denominator as b, you have the log property, which is ln of a over b. Ln of a over b will be ln of a minus ln of b. Yeah? So treat the numerator as a and the denominator as b. So when you're expanding this using these log properties, it's going to be ln of a, my a, it's a numerator, e to the 5x times sine 2x minus ln of b. And b, we said we treat our b as a denominator. So ln of b, 3x, I can write the square root of 3x squared plus 2 as 3x squared plus 2 to the power of half. And we're applying the log properties here. It's multiplied by tan 3x. Okay. So this is ln of a minus ln of b. This is b. We still see one of the properties here, which is, okay, this is the first log property. Okay. We see this property, which is ln of a times b. Yeah. Ln of a times b is same as ln of a plus ln of b. So here we still see this property, ln of a times b, if we treat our first function as a and second function as b. So we can apply this property. So here I have ln of y equal to ln of e to the 5x plus ln of sine 2x. I just apply this log property. So yeah. And also I see the same property here in my second term. So I can expanding, treat this as a and this as b. This would be ln of a plus ln of b. So this would be, okay. Let's open a bracket because I'm going to introduce two terms. So this would be ln of 3x squared plus 2 to the half plus ln of the b, ln of tan 3x. I still see another property here. The next property, if you have ln of a is to the r, you can take r down. This will be r ln a. So I can see I have ln and treat this as a to the power of r. I can take this r down here. So now the second step, we still see this log property here. So ln of y equal to, let's take this down, 5x multiplied by ln e. But we know ln e is 1, so anything multiplied by 1 will come as it is, plus ln of sine 2x. And here, let's multiply this negative inside. We're going to have minus, but you still see this log property. We can take this r down, treat this as r, let's take it down. So this would be half ln of 3x squared plus 2. And again, we can multiply negative here, this positive with minus, ln of tan 3x. Okay. Okay. Here we have our function y. My function y was a product and quotient of more than two functions. That's why we're using a log differentiation. And the first step was to introduce ln on both sides. Ln of the left-hand side equal to the ln of the right-hand side. That's the first step. And second step, expanding your right-hand side using the log properties. So we see here ln of the numerator over denominator. Ln of the numerator over denominator is same as ln of the numerator minus ln of the denominator. So ln of the numerator minus ln of the denominator, ln of a minus ln of b. And then we also see the second property, which is ln of a times b. If we choose the first function as a and b, so this will be ln y equal to ln of e to the 5x plus ln of sine 2x minus ln of the first function, which is 3x squared plus 2 to the half, plus ln of the second function, ln of tan 3x. And then we still see one of those three properties, still see. So here this was this property, which is ln of a to the r, and then we can take this r down. So this will be r ln of a. So ln of y will be, we take r down here, multiply by ln e. Ln e, we know it's 1, so anything multiplied by 1 will come as it is. So 5x times 1. And we return this second term, ln of sine 2x minus, we take also, apply this log property, we take this half down. At the same time, while we multiply by negative inside, yeah, we get this term, and then multiply the negative to the second term. So it will be negative here. So based on our differentiator, we will still applying the log properties. After you expanding completely, now you differentiate. As you can see, now this is the implicit function. Y, variable y is not alone on one side. So y is a function of x. So we apply what we call implicit differentiation. Differentiate both sides, each term, and treat y as a function. Here on the left-hand side, I want to derive in ln of a function. Okay, so the derivative of ln y will be 1 over a function y times a derivative of the inner function. Derivative of y is dy dx equal to the derivative of each term. So derivative of 5x is 5 plus a derivative of ln of a function. Let me write this property, this standard derivative. It will be given to you if we're deriving ln of a function. This, oh, okay, sorry. This equal to 1 over a function times the derivative of the inner function, or you can write this as f prime over f of x. This standard derivative will be given to you. All right, let's continue. I'm deriving ln of sine 2x, ln of a function. So the derivative is 1 over a function times a derivative of the inner function. So the derivative of sine of a function is going to be 2 cos of 2x. Okay. Minus half times the derivative of a ln of a function. The derivative of a ln of a function is 1 over that function, in this case is 3x squared plus 2 times a derivative of the inner function, which is 6x. And minus derivative of, again, it's ln of a function. This is going to be 1 over a function 3x times the derivative of the inner function. Derivative of tan of 3x is going to be 3x squared 3x. Solve this. Okay. Next, remember we want to find dy dx. To find dy dx, we solve for dy dx. you can just multiply by y all times. Okay. So if I multiply by 1 on the left hand side, you see it will cancel. We're going to left with dy dx equal to, again, y multiply all terms on the right hand side. So y multiplied by 5 plus 2 cos 2x over sine 2x. This is minus 2 will cancel with 3 2's here. We're gonna left with 3. This would be 3x over 3x squared plus 2 minus 3x squared 3x over sine 3x. Okay, so I was multiplying y with everything on the right hand side. And in log differentiation, in implicit, you can leave your derivative in terms of x and y, but in log differentiation, y is always given here. As you can see here, your y, it was just the function that was given to you. You see y is equal to this function that you want to find the derivative. So at the end of your derivative, if you see your derivative is in terms of y, in log differentiation, I'm saying substitute back this y here because it's given. If you check, y is e to the 5x sine 2x over square root of 3x squared plus 2 times sine 3x. This is my function y. I substitute here y equals it multiplied by 5 plus 2 cot 2x, and there's no max for this. I will give you a full marks up to this step. I won't expect you to write cos of 2x over sine x as cot 2x, so you can leave it here if you forgot this identity. Minus 3x over 3x squared plus 2 minus 3x squared 3x over sine 3x. Okay, this is my dy dx. That's how you find the derivative in log differentiation. Just to recap what I said, you introduce ln on both sides and expanding your right hand side using the log properties. After you apply those log properties and differentiate implicitly, treat y as a function of x, you know always the derivative of y is dy dx. And then that's how you find the derivative. Thank you. Okay. All right. Let's look at the example 2. I want to find dy dx if my 1 is a function of x, my y is equal to ln of x squared cos of 2x over square root of 2x plus 1. Okay, as you can see here, my y is ln of a function, and ln here is already given. You don't have to introduce ln. If you have ln of the product or a quotient, even if it's 2-factor function, as long as you have ln, just apply the log properties. We don't have to introduce ln here, but there's ln, but it's ln of the product and quotient. It can be 2 times 2-factor function or quotient of 2 function, but in this case anyway, there are 3-factor function, ln of 3-factor function. So, but if you see a log property, even if ln is given, just apply the log differentiation. Yeah. So solution here. Okay, we have y equal to ln of a product and quotient of functions. So just apply the log properties first before you differentiate. So you don't in this step you don't have to introduce ln. So y is equal to, I see this property, ln of a over b equal to ln of a minus ln of b. I see this property, ln of a over b, treats my numerator as a and my denominator as b. This will be ln of a minus ln of b. So this will be ln of a is my numerator function, ln of x squared cos of 2x minus ln of square root of 2x plus 1, my denominator. And also I can still see one of the three properties that I gave you, ln of a times b. This is ln of a plus ln of b. I still see this property here in my first term, ln of a times b. I can treat my first function as a and b and then just apply this log property. So my y will be ln of a, which is x squared, plus ln of b, which is my second function, minus ln, I can write square root of 2x plus 1 as 2x plus 1 to the power of half. Change the square root to the power of half. Okay, let me apply this property. The last one. The last property is this one. If you have ln of a and a is to the power of r, this is equal to r ln of a. So I can treat this as r and take r down here. So this, or even here I said this property in my first term. Okay, this would be y equal to, apply this property, take 2 down, ln of x plus ln of cos 2x minus, apply the property, half ln of 2x plus 1. Yeah, now I expanded my right hand side completely, or I just apply the log properties where I see one of these three log properties. So now I'm ready to differentiate after applying the log properties. So dy dx will be 2 1 over x, derivative of ln x is 1 over x, plus, and derivative of a function, derivative of ln of cos 2x, it's 1 over that function, my function is cos 2x, times the derivative of the inner function, derivative of cos 2x is minus 2 sine 2x, minus, let me put this in brackets, okay? And derivative of this is 1 over 2. Derivative of ln of a function is going to be 1 over 2x plus 1 multiplied by the derivative of this, which is 2. So my dy dx is going to be 2 over x, here minus 2 sine of 2x over cos 2x. I can see 2 cancel with 2, I'll left it 1, minus 1 over 2x plus 1. So this is just my dy dx. I started by applying the log properties because I see ln. So if you see one of these properties, even if there are two factor function, if you can apply the log property, just apply. So where you see ln, it's better to apply the log properties first before differentiating your function. Okay. I want you to try this as an exercise. I'll give you a hint here. Try this as exercise. Find dy dx if my function y is equal to e to the x times ln x times sine of 2x plus 3. You see here, ln is not given, and you see your function y, it's a product of more than two vector functions. As you can see, how many functions? 1, 2, 3 vector functions. So we need to apply the log properties. So as a hint, the first step, you apply the log properties, apply the log differentiation. So in here, they didn't like give you ln, so you introduce ln on both sides. Ln of the left hand side equal to the ln of the right hand side. And then expand your right hand side using log properties. So ln of y equal to ln, can first treat the first two functions as a and the second function as b. So this is a multiplied by b. Ln of a times b is same as ln of a. I set my a, this first two function, plus ln of b. Sine of 2x plus 3. Yeah. Because anyway, those two functions, they multiply with this, so I can treat this as a and b and apply the log property. And next, ln of y, I can still see one of the log properties, ln of a times b. So ln of a plus ln of b, ln of ln x, plus ln of sine 2x plus 3. Okay. So yeah. So yeah, I can still see one of the three properties that I gave you earlier. So ln of a to the r, I can take r here. So ln of y equal to x times ln e is 1. So it will be x times 1 plus ln of ln x plus ln of sine of 2x plus 3. Okay, so I want you to continue. Find dy dx. You should know how to differentiate this. Okay, thank you so much. And the next, it will be a last part of log differentiation where we have a function to the power of a function. Yeah. Okay, thank you so much. All right, guys. And the last section of log differentiation, it's when we have a term in our function which is a function to the power of a function. For example, let's say we want to find the derivative dy dx of y equal to x to the power of x. We don't have a standard derivative of this form. How can you derive x to the power of x? We don't have a standard derivative of a variable to the power of the variable, or it can be a function to the power of a function. So if you have a function with a term that is a function to the power of a function, we apply a log differentiation. So here, the first step, a solution. Okay. Okay. We want to derive y equal to x to the power of x. The first step is to make sure a term with a function to the power of a function is alone on one side. In this case, a function to the power of a function is alone on one side, on the right-hand side. So we could with that. And the second step is to introduce ln on both sides. Our aim of introducing ln, we don't need this power function here down here. So when we introduce ln, it's going to be ln of the left-hand side equal to ln of the right-hand side. And with log properties, now we can able to take this down, apply this log property. Ln of a to the r, ln of a, and a is to the power of r. We can take this r down. This will be r ln of a. So this will be ln of y equal to, this is r and this is a. We can take r here down. So this will be x times ln of x. Okay. We apply log differentiation by introducing ln on both sides. So we can take this power function. Our aim is just to take this power function down here. Okay. And then after you take your power function, you're ready to differentiate this implicitly. And remember, you treat y as a function of x because y is a function of x. So derivative of the left-hand side, derivative of ln of y, ln of a function, derivative will be 1 over your function y times a derivative of the inner function dy dx equal to the derivative of the right-hand side. You see here on the right-hand side, you want to find the derivative of the product of two functions of x times ln of x. So let's apply the product rule here because we're differentiating. Derivative of the first is 1, derivative of x. Leave the second, ln x, plus, now leave the first, multiply by the derivative of the second, it's 1 over x, the derivative of ln x. Next step, remember we want to find dy dx. So you need to solve for dy dx. What you can do is just multiplying by y on both sides. Every time multiply by y. So on the left hand side, if we multiply by y, y will cancel. So we'll have dy dx on the left hand side equal to y multiply everything on my right hand side. So this will be ln x on my handwriting. We multiply y with everything on my right hand side. It will be y multiplied by ln x plus 1 because x and x will cancel there. Remember, I told you in log differentiation, y will be always given. So after you derive, you need to substitute back your y. Your y was your given function. Y is x to the power of x, ln of x plus 1. Okay. So this is the derivative of y. My y is this function of s. We're finding this derivative. We apply the log differentiation. Our aim is to take this first down, so we're able to differentiate this function. That's why we introduce first log, and then we take this power function x down. Yeah. And then you follow this step. Okay. And this was the first example. Let's look at the second example. Example 2. Let's say now we want to find dy dx of y equal to e to the 2x plus 6x to the power of tan x. Okay, I want to find the derivative of this function. As you can see, I have a function to the power of a function term. It's alone on the right hand side. But to find the derivative of this function, we need to use the log differentiation. Yeah? So we need to apply ln on both sides. Solution. So ln of the left hand side equal to ln of the right hand side. Right hand side. Okay. So far we have this. Our aim is to take this power function tan x down here. So this will be ln of y equal to, let's take now this function, power function, which is tan here. So this will be tan x multiplied by ln of e to the 2x plus 6x. After you bring down your power function, you're ready to differentiate. Differentiate both sides. Each time apply the implicit. Derivative of the left-hand side is derivative of a ln of a function. Derivative of ln of the function is 1 over a function y times derivative of the inner function, derivative of y is dy dx, equal to the derivative. Always here in a function to the power of function, when you're deriving your right hand side, it will be a derivative of the product. So you're gonna always apply the product rule. So the product rule say derive the first, which is derivative of tan x, it's sec x squared x. Leave the second function, ln of e to the 2x plus 6x, and then plus, now we leave the first and deriving the second. It's ln of a function. Derivative of a ln of a function is 1 over a function e to the 2x plus 6x times the derivative of the inner function, which is 2e2x plus 6. Derivative of e to the function is the derivative of the inner function, which is 2 times e to the function. And plus the derivative of 6x is 6. Okay. So this is my derivative. But remember, I want to find dy dx. So I don't need this 1 over y. So I need to solve for dy dx. So I'll need to multiply by y on both sides. What you do on the left, you need to do it on the right. But when we multiply by 1 on the left hand side, you see y will cancel. So I will have dy dx equal to y. Multiply everything on my right hand side. So y multiply everything on my right hand side. Sec squared x ln of e to the 2x plus 6x plus tan x 2e 2x plus 6 all over e to the 2x plus 6x. Okay. Remember, you don't end here. This is your dy, but remember in log differentiation, I told you y is always given. So y, this y is this function. You say y, this is y. So you always need to substitute this function at the end. The derivative in log differentiation should be only in terms of x. So here, the final answer is when we substitute y. Y is, we said it's e to the 2x plus 6x to the power of tan x. And multiply by sec squared x, we return everything. Ln of e to the 2x plus 6x plus tan x times 2e to the 2x plus 6 over e to the 2x plus 6x now. Okay, so this is your final answer, the derivative of your function y. Okay. This was the second example in log differentiation. Okay. And the third example here, let's say we want to find dy dx if my y now is sine x to the power of tan x. Okay. Now this is the third example now. What I'm doing now. I want to find dy dx if y is equal to sine x to the power of tan x. Let's say, no, let me do this example, the hard one. Let's say my function y is tan x to the power of x squared plus x. I want to find the derivative of this function. Okay, I want to find dy dx if my function y is equal to tan x all to the power of x squared plus x. Okay. Again, you see my function y has the term which is a function to the power of a function. Okay. So we obviously going to need to apply log differentiation. But in this case, our first step, remember I told you, if you have a term which is a function to the power of a function, you make sure the term is alone on one side. So we can leave this term which is a function to the power of a function alone on the right hand side. So the first step is to make sure your function to the power of a function is alone on one side. So we need to take this term x to the left hand side. So that's our first step. So y minus x is equal to tan x to the power of x squared. This is your first step. And then your second step is to take your power function down, this power function down. Always, this is our aim. So by introducing ln on both sides, ln of the left hand side, so ln of y minus x is equal to a ln of the right hand side. Okay, we introduce that ln. So now we're able to take this power function down here. Okay, so ln of y minus x, we turn the left hand side. And on the right hand side, we can apply this property ln of a to the power of r. We can take r down here. So this will be x squared ln of tan x. Okay. After you take your power function down, always you're ready to differentiate your function. So let's differentiate the left hand side. We have ln of a function. The derivative of the ln of the function is 1 over a function. My inner function is y minus x, and multiplied by a derivative of the inner function, especially if the derivative have more than one term. I said always it's safe to put them in brackets. Don't forget brackets. Some of you lose mark because of they forget brackets. So derivative of the ln of a function is 1 over a function multiplied by a derivative of the inner function. So the derivative of this will be dy dx, derivative of the first term, minus 1, So equal to the derivative of the right hand side. I'm deriving, so I'm deriving implicit, so I'm deriving both sides. Okay, so this is what the derivative of the ln of a function. It's 1 over function times the derivative of the inner function equal to a derivative of this. As you can see, this is a product of two functions, x squared multiplied by ln of tan x. So the derivative, we apply the product rule. So derivative of the first is 2x, while we leave the second, plus, now we leave the first and deriving the second. Derivative ln of the function is 1 over a function. In this case, our inner function is tan x times derivative of tan x, which is sec squared x. Okay, so this is our derivative, but we need to see what is dy dx. So we need to solve for dy dx. So the first step here, we agree we need to multiply by y minus x all times, so we'll able to cancel this term. First, we're solving for dy dx. So when we multiply by 1 minus x on my left hand side, it will cancel, so I'm left with dy dx minus 1 equal to, remember I'm multiplying by 1 minus x, left hand side and right hand side. On the left hand side it's cancelled, so on my right hand side this y minus x will multiply everything on my right hand side. So y minus x, it's multiplying 2x ln of tan x okay, plus x squared sec squared x over tan x. Okay, remember I'm solving for dy dx. I need to see what is my dy dx. The question, they said find dy dx, so I need to know what is dy dx. So, to solve for dy dx, I'll need to transpose this minus 1 to the right hand side, so it will change sign. So I'll see dy dx will be y minus x multiplied by 2x ln of tan x plus x squared sec squared x over tan x, and then we transpose it minus 1, so it will change sign to be plus 1. So this is my dy dx, but the derivative in log differentiation should be in terms of x. So when you see y is given, okay, it's a given function, this function. Say y is given this function, so you need to substitute back at the end if it's in terms of y in log differentiation. In implicit differentiation, it's fine, you can leave in terms of x and y, but in log differentiation, substitute y in your final step. There's a mark for this. So this dy dx, this dy dx would be y, my y we said is tan x to the power of x squared plus x. Okay, this is my function y, you remember, and don't forget this minus here. So this is my function y, this function y minus x. Okay, and multiply everything on the right hand side. X squared x over tan x and plus 1, and you notice this x cancel with x, so your final answer will be tan x to the power of x squared. and it's multiplied by 2x. So this is x. 2x ln of tan x plus x squared sec squared x over tan x plus 1. All right. Thank you so much. And this is the end of derivatives. End of derivative. The next chapter we're going to do application of derivatives. Okay. And I will send also the exercise through a class wrapper on this section of log differentiation. Okay, thank you so much and good luck, everyone.